Good evening, friends. This is Tulsi Bisain, and today we will continue our presentation on the optimizers. So, yesterday we have completed ADA grade, the optimizers, which used the updation of the learning rate, and we are setting the learning rate at 0.9 in that case. And the advantage and disadvantage of the ADA grade was that the learning rate are manually means adjusted according to the iteration, and the disadvantage was the iteration. If the iteration is become very the more iteration will be more, then the learning rate will be decreases, and that will arise the problem of the slow convergence and the vanishing gradient problem. So to overcome this problem, we are using Adadelta. So in this ADA grade, the learning rate, we are also working on the learning rate, and here the more robustness happen in the Adadelta. This is the extension of Ada grade, and here we are fixing the learning rate at a very minimum level, and so that the and in Adadelta the updates are comparatively very frequently compared to Ada grade, and we are not initializing any learning rate here. So this is the Ada delta, which is just the extension of the Ada grade, but not very much different from it. And here, so this is the formula for Ada grade. You can see, sorry, Ada delta. You can see here. Here we are getting the square term of this, the gradient. Okay. Our next optimizer is RMSprop. RMSprop is this formula is the same as the Ada delta, but here the it is trying to balance between the step size for the momentum, which we have seen earlier in the optimizer. So here there is a large gradient, then this decreases the size of the momentum to generally for solving the problem of the exploding or the vanishing gradient problem. So here it divides the learning rate exponentially, and it calculates the exponentially decay average, and generally this sets the learning rate as 0.001. So RMSprop and the Adadelta have the same development strategy, but here the learning rate is little bit different, and this reduces the learning rate. So therefore, the execution is faster than the Ada grade, and this slowly decreasing the value of the learning rate. You can see the formula. So formula for the Ada delta and RMSprop is nearly equal to each other, but the updation strategy is different for the learning rate. Now next is adaptive moment estimation, that is ADAM. ADAM is the most popular optimizers which we are using. It is the combination of RMSprop and the stochastic gradient descent with momentum. So it uses the adaptive learning rate for each parameter and also calculating the exponential decaying average. And we have already seen that in the ADA grade. So we are working on the just a recent update, and we are not storing the past updates. So here also the gradients average are calculated on the past squared gradient. Here we are squaring the gradient value of the Ada gradient Ada delta, and which we use the term VT for that. Adam is also keeps an exponential decaying average, okay, for just the past gradient which is related to momentum, and that is we are showing by the MT. Okay, here momentum can be seen like we are throwing a ball in the slope, and the ball is going towards the local minimum value with the reducing oscillations. So we can compare that example here. And here also we are using some hyperparametric tuning with the coefficients beta 1 and beta 2 that belongs to 0 to 1 value. And here the ADA grade, ADA delta, RMSprop, and the ADAM. This all are we are calculating the gradient descent in an exponential way. Okay, and we are calculating the how this gradient descent differences are where going smaller than we are going to throughout the network, and we are trying to reduce our loss functions also. So this is time stamped with the momentum, and this is the previous gradient average values with respect to beta 1 and beta 2. Here G is the gradient average we are calculating. So so these are the values. Now we have seen various algorithms like gradient descent, stochastic gradient descent, mini Bayes gradient descent, momentum gradient descent, ADA grade, ADA delta, and the Adams. Now, which algorithms we should choose for our model? Also, you can see the diagram here. So this purple one is the Adam. So this oscillations showing the iterations and the differences of the convergence direction. Okay, and this in Adam you can see here the loss function is reduced comparatively the other optimizers, and this is the ADA grade blue one. You can see here the figure. So now the based on this figure, we can conclude some of the points that in SGD algorithm, this is stuck at the saddle point. So SGD algorithm can only be used for shallow network, means where the graph is not very much variant, means ups and downs are not much there in the respect to SGD, because there is a problem with respect to SGD is that it stuck at the local minima, means when it comes down and it find a local minima, then it stuck there. But suppose in the further way, if there is also a local minima, then it cannot get that. Okay, so that is the problem of the SGD, and the red one here, that SGD showing here. Now next was the it converges very slowly, and Adadelta being the fastest following the momentum. Ada grade and Adadelta can use for sparse data. Sparse data means if there is a very scattered or different form of data, then where there can we use Ada grade and Adadelta. Momentum and energy that works well, but their convergence rate is slower. Animation for Adam is that we have already seen the visualization of the Adam also, and this is the fastest algorithm to converge to minima. And Adam is considered the best algorithm among all the algorithms. So popularly, RMSprop and Adam are the two optimizers which we are using according to our data set, and they are heavily used today. So these were the very brief introductions of the all the optimizers. If you are having any doubt, then you can ask. Okay.
No doubt, Tulsi.
Okay. Thank you.